So I'm Dan Smith. I'm one of the committers on the Geode project. And I'm going to be talking to you a little bit about how Geode works. But first, this is a photo from the last time I was in Austin. And it's actually breaking open one of those little geodes. I was actually here with some other Geode committers, and we spent maybe half an hour wandering around Austin trying to figure out how to open this thing. So there's some really triumphant people there standing holding that thing. But we were actually here for something really cool, because 4 years ago, Geode actually went from being a closed source project, Gemfire, to an open source project when we got donated to the Apache Foundation. And we were here in Austin celebrating the fact that it's now an open source project and talking about it to a much tinier room than this at ApacheCon about this new project called Geode. And I, for one, really like working for this kind of open source, open governance type of project where all of you in this room can come and join and work on the source code or get involved in the actual running of the project if you want to. So I would like to say, just starting off, for all of you, if you're new to this community, welcome to the Geode community. And I hope that it doesn't take you quite as long to get involved in Geode as it did for us to get into that Geode. So, oh, hello. A little bit of feedback. Oh, okay. Everybody's phone is going off at once. If you see any cars, just let me know. So before I start off, I think some of you folks may not know what Geode is. Maybe you just walked into this room because you had some spare time this morning or this afternoon. So I wanted to walk you through a little bit about what is Geode. First of all, Geode is a key value store. We're a distributed key value store. So you have some, oh, is that not showing up for you guys? There we go. Okay. Can you see that? All right. So we're a distributed key value store. So you have a bunch of servers, and then you have, basically you can store keys and values. And we're really focused on a specific space for what kind of data we handle. We're really focused on operational data, and we're focused on having a couple key properties. So one of those properties is that we're highly available. So if you have a server crash, and assuming you've configured redundancy, your client will just keep working. It'll automatically fail over for you. And you won't, hopefully your application won't notice. But your operator or your platform will and can restart that server for you. The other thing we're really focused on is being a low latency data store. And for us, this really means a couple things, like minimizing the amount of I/O that it takes to do your operation, and minimizing the amount of locking and blocking and context switches that it takes to do your operation. So if you're Googling Geode right now on your laptop, hopefully you're just listening to me, but if you're doing that, you might see Geode as like an in-memory data grid or in-memory data store. We talk about in-memory a lot. And that's really about minimizing the I/O. We're saying we'll keep most of your data in memory and we'll get it back to you at in-memory speeds. But we actually do have persistence and all that stuff too. We just talk about in-memory a lot. And finally, if you're a fan of the CAP theorem, which says data stores can be either consistent, available, or partition tolerant, pick two of those things. We lean towards the consistency and partition tolerance. So that means that if Trogdor comes and burninates your network, then we will potentially take some of your data offline in order to make sure that it stays consistent. So this is, our model is we're focused on consistency and keeping your data consistent for you. So in Geode, we talk a lot about these things called regions. And regions are just named maps. So if you're coming from a SQL world, you can think about a region like a table. And we have two types of regions. One of the types is a replicated region, where every server has a copy of all the data in the region. So if you add more servers, you get more copies. And this is good for data that's kind of, you maybe don't have a lot of it, but you want it to be available everywhere. And then the other type of region we have is what we call a partitioned region. And with a partitioned region, we're doing partitioning or sharding of your data so that each server has a different slice of your data stored on that server. So and then you can add more servers to scale out your capacity. In Geode, when we talk about a key value store, our keys and values are actually objects, or actually graphs of objects, complex graphs of objects. So you can basically store Java objects or C++, C#, JSON documents, and we have a serialization layer that kind of manages compatibility between all of those things. So you're not just storing blobs, you're storing these complex objects. And we have a whole lot of other features that I'm not going to get a chance to talk to today because I don't have time, but you can see some of them on this slide. So you can do indexes and querying on those graphs of objects, continuous queries, transactions. We have persistence, WAN replication, a lot of other stuff. Hopefully some of the later speakers are going to cover some of these things. But for us, I really wanted to focus on just one piece of Geode to get a little bit more in depth about how it actually works. And the piece I chose to focus on is partition regions. So we're going to look into these and see how we really get those properties of high availability and consistency with partition regions. We're going to assume that we have something like a membership system and a distributed lock system. And maybe in another talk sometime, somebody else can talk about how those work. So what we are really going to look into is how do partition regions actually do partitioning, how they give you high availability, how they keep your data consistent, how we recover from failures, and how we do rebalancing and distribute your data so that you have the lowest latency that we can give you. So for partitioning, the way we do partitioning is actually really simple. We basically just hash your data. So when you do a put with Marie Tharp as a key, we take the hash code and we mod it by some fixed number of buckets, and that gives us the bucket that your data stays in. So in this case, it's going to bucket 2. And then we take these buckets and we distribute them amongst the servers, and that's basically where your data is stored then. So based on the hash code of your key, that gives you a bucket, and then that bucket is stored on a particular server. And there's a little bit more complexity there. It doesn't have to be the hash code of your key. You can kind of control that, but this is kind of the simple model. So there you go. You know how partition regions work. It's pretty simple, right? Well, I guess there's a few things that we probably still need to talk about. We didn't really talk about how the data actually found its way to that particular bucket and that particular server. We didn't talk about handling failures yet. We didn't talk about how we make sure that your data is consistent, how we replace lost copies of your data, or how we actually improve the balance of your data. So let's look at some of these things. And let's look at that first one. So how do we get data into the bucket? So when we were designing partition regions, or I should say when the people before me were designing partition regions, they were looking at, okay, how can we do this? And they decided to call on one of our common programmer superpowers, which is laziness. You functional programmers probably know what I'm talking about here. So when the server initially, or when the system initially starts up, we have no buckets. We're really lazy. Things just start up. And the client has no idea where anything is. So initially, everything's empty. And when you do an operation, like a put, the client just sends it to some server. It doesn't really care what. Actually, there's a little bit of complexity there. We actually have some smarts about finding the least loaded server, but for our purposes, it just goes to some server. And then that server is going to lazily tell another server, potentially, to create that bucket based on actually the best place to put that. And I'll talk about what best means in a little bit. But it's basically going to tell that server to create the bucket and store the data. So your bucket and your location for the data is lazily created when you're doing an operation. And then, as part of the reply to that operation, the server is also going to tell the client, okay, you sent this operation to me, but I wasn't the best place for you to do this operation. Like, I don't have this bucket, it's somewhere else. You need to update your metadata. And at that point, the client is going to turn around and fetch metadata from one of the servers to say, where are all the buckets at this point? So it's basically lazily discovering the metadata and storing it in a routing table on the client. And the reason why we have kind of this lazy process on the client is that the location of buckets can be changing all the time. If you do a rebalance, the buckets can move. If you have a server fail and have it start another one up, the bucket locations may be changing. And so we always have this ability for the client to be sending stuff to the wrong places and then lazily discover, oh, there's new bucket metadata that I need to download and update my routing table. And this is also one of the ways that we make sure that you have the lowest latency we can give you, because in my previous slide, we were doing an extra network hop to go through this proxy server, and now we get to go directly to the server where the data is stored. So there's our next put going directly to the location where the data is stored. Okay, so I told you that Geode is highly available. So we also have to handle failures in some way. And in order to do this, we called on another common programmer tendency, which is duplicating work. So in our case, this means that we don't just have one copy of your bucket, we actually have another copy of your bucket. So whenever well, it's based on your redundancy settings, but assuming you've set up redundancy, we'll make extra copies. And one key thing here is that we actually distribute to all copies of your data before returning to the client. And what that lets us tell you is that once your operation is done, if you turn around and do another read, you're guaranteed to see the result of that operation. And that sounds kind of obvious, like you'd think, okay, if I do an update, I should always see the result of that update, but that's actually not the case for some distributed systems, because you could conceivably have a system, or some systems actually replicate asynchronously, and then you can read from the wrong copy and get sort of stale data. So we are trying to make sure that you see the most up-to-date data. And then obviously having a copy doesn't really help you unless you can actually use the other copy. So we also have failover, so the client will automatically retry to the other copy if there's a failure of the primary copy, or one of the copies. So. All right, so now we have high availability, but by adding extra copies, this introduces a whole new set of problems, because now we have 2 copies of your data, and the question is, are those copies the same? Are they consistent? Because as soon as you have 2 copies of something, you have a distributed consensus problem. You have to make sure that those copies agree on what's actually stored in there. So now that we have this, we have to figure out how we can make these copies the same. And just to give you an example, so here's one of the ways it can go wrong. If we were to let you write to either copy and we weren't smart about it, you could have a case where different clients write to different copies, different values to different copies, and those values could actually maybe sort of just pass each other in the network and end up with the different copies being inconsistent. So in this case, one copy has value 2 and the other copy has value 1, and that would be bad, and we don't want that to happen. So the way that we solve this is actually another common programmer tendency, which is waiting in line. So rather than letting everybody write to different copies, all the clients actually have to write to a primary copy. And this is kind of how we cheat on the distributed consensus problem, at least at a partition region level, is we can actually lean on our lower layers, like our distributed lock service, to have a unique primary. So in this case, one of these servers both try to get a lock, and one of them will get a lock and become the primary. And then all the operations are going to go through that primary. And in addition, on that primary, we are making sure that for a given key, the operations actually happen in order for that key. So we actually lock the key while that's happening and while we're doing distribution, so that if these 2 clients put different values for the key, those 2 puts will happen in some serial order. So either the first put will completely finish or the second put will completely finish. And because these operations get applied in the same order on both servers, they end up with the same result at the end, and so they're consistent. There's a slightly more subtle consistency problem that actually comes out from doing failover. So I mentioned that normally for a successful operation, we're going to wait for that operation to completely finish. But if there is a failure, then there may still be work happening in the cluster as kind of on behalf of the server that crashed. So the server that crashed might have initiated replication to some other servers, but then it crashed and we retried. And that replication can actually sort of be floating around through the system, not yet processed. And that can cause us to basically have an old lingering event show up in secondary copies or much later on in time. And so the way we actually get around this is we have this concept of an event ID. So every operation that starts from a client gets an event ID associated with it. And then when it's retried with the same event ID. So that if we have this old lingering operation sort of floating through the system, it has this old event ID associated with it, and we have an event tracker that can basically discard it and say, I've already seen this event. I don't have to do anything with it. So I won't apply an old event and go back to an old state of the system. So there's another consistency problem, which we have to talk about. I mentioned we did also as a consequence of failure. So going back for a sec, jump back. Sorry, where's my failover slide? Okay, so when we have a server failure, the question is really, how does the other server, server 2, detect that failure? It's doing that by monitoring the network, right? That's the only thing that it has access to. It can ping the other server, it can listen for traffic from the other server, can look for all those things. So the problem is that there's really, sorry, I should have jumped here. Okay, so there's really two different cases. Maybe that server is failing, or maybe my network is what failed and the server is still alive. And maybe I can actually have a case where my servers are both still alive and they have some subset of the clients talking to them, but they can't talk to each other, so they both think that the other server failed. So this is what's called a split brain. And in this case, we end up with two primaries that end up with inconsistent data, which we wouldn't want to have happen. So Geode uses a clever technique for avoiding this, which I like to call giving up. So what this actually means is that we, at the membership layer, we have a network partition detection algorithm. And what it's doing is it's checking to make sure that when we see a failure, if we see more than 50% of the system fail from our perspective, so we see more than 50% of the system go away, we will shut ourselves down instead. We'll give up rather than becoming primary and being the wrong copy. So that means that basically you're always going to have, if you have 51% or more of your system running, then it can keep running. But if you don't, then we'll just shut down. And this will make sure that your data is consistent and we don't end up with different copies of your data, or copies that are inconsistent. Okay, so when we have a failure, we also, it's not good enough just to keep running. We need to replace the missing copy of your data. And there's different ways to configure that. I'm going to talk a little bit about when you've set things up to replace the lost copy immediately after there's a failure. So when you do this, we can basically make extra copies with the remaining servers. But we have a little bit of a problem because we want this to be smart. We don't want one of those servers to grab all of the copies of the data, for example. So we kind of have a coordination problem where we need to be really smart and put things in the right places. And we do this by telling others what to do, or actually having everybody tell everybody what to do. So I'm going to walk you through how this works a little bit. So initially, when there's a failure, we have this component called a redundancy provider, and it's actually going to kick off on all of the servers at once. Everybody's going to try to do redundancy recovery. But one of those servers is going to get a distributed lock, and that's going to prevent the other servers from doing anything for the time being. And then it will go and tell all the other servers what to do. So it'll say, okay, where's the best place to make a copy of this bucket? And it'll tell that server to copy the bucket. That server will make a copy, and then so redundancy will be completely satisfied. At that point, once it's done, once server 4 is done doing its work here, it'll release the lock, and the next server will get the lock and try to do the same thing. But because all the work has already been done, this is really cheap. It says, oh, there's nothing to do. Finally, the last server gets the lock, still nothing to do. So using this technique, we get this cool property that we have a really smart coordination, so we can put the buckets in the best places we possibly can. But we're also guaranteeing that redundancy recovery is highly available and it will always happen. And it's okay to do it everywhere because all the subsequent implications are cheap. Okay, so finally, this last one, how do we get the best data distribution we can? And how do we move data to servers that start up if you want to expand the size of your cluster? So for this, we called on another property that we have, or another thing that we programmers like to do, which is being greedy. Or in this case, actually using a greedy optimizer. So let me kind of show you how this works. So I'm going to walk you through how we actually move data to other servers. So the way we actually do this is with a cost-based optimizer, where in this case, our cost function is basically the variance in the amount of data stored on each server. So you kind of see I've computed the variance of this cluster up here is 1,600. And then we have a greedy algorithm that will basically do one operation, like one move of a bucket at a time, that will make the largest improvement in variance for the least amount of data moved. So I might move this bucket because it's a smaller bucket, but I get a bigger improvement in variance. And I might move that bucket. So when we're rebalancing and moving your data, that's what we're doing, is using this cost-based optimizer. And actually, this is the same optimizer that's used by the redundancy recovery that I just talked about a couple minutes ago. In fact, rebalancing and redundancy recovery are actually the same code as far as we're concerned. So we have one thing, this partition region rebalance op, if you go look at the code, that goes through these 3 phases. So when you do a rebalance, it does all 3 phases. So first, it restores redundancy. Next, it moves data to optimize the distribution of data. And finally, it switches primaries around to optimize the distribution of primaries. So that's what happens when we do a rebalance. When you're doing redundancy recovery, it's the same code. It just does phases 1 and 3, and that's it. It doesn't move the data because that might be a little bit more expensive and something that you don't want to do at that time. And the other thing that we do is that if you have any membership changes in your system while this is happening, we start over from the beginning. So this is how we make sure that we're not making your system worse while we're doing all this optimization. We're always basing it on the most up-to-date data, and we're always making the one best move at any particular point in time to improve the distribution of your data in the system. So finally, you'll get to the best distribution of data that we can according to that cost function. So let me wrap it up. I think we learned a little bit about partition regions. We learned that they use a really simple algorithm, really simple idea, which is hashing and hashing data to buckets. But we really had to call on some of our superpowers here of laziness, duplication, bossiness, and greed in order to accomplish the properties that we wanted to have, which is high availability, low latency, and consistency. So thank you very much. And I think Jag is going to come up to introduce our next speaker. Thank you.
Well, thanks a lot for the beautiful presentation. It was really good. My question was, you covered the write logs. So while writing or putting data into the table, you get a lock. So would it also affect the reads for that key at that time?
Right, that's a really good question. So I think maybe your question is, do we also have to get a lock to do a read? Is that right?
Well, during the write.
Oh.
So if you're writing for that key,
mm-hmm.
and if a request comes in to write that key during that time, would you do a read lock as well? Or will that lock affect the read as well?
Yeah, okay, so that is a good question. And actually, it doesn't. So reads don't have to get in line behind the writes. So I guess I should have said, I didn't say, that we actually do let reads go to either copy. So your read could go to either the primary or the secondary. And we will actually return you that data immediately at that point. So when you're doing that read, there may be an operation in progress, a write operation in progress, and you may see the new value of that write operation, or you may see the value before that write happens. But because your write is already in progress, you don't know which one you're going to get, right? So yeah.
All right. So then, in that case, the primary table or the routing table,
mm-hmm.
whenever there's a write request, it updates the routing table for the read to go to the secondary. Because if the read comes in to the same server where the write is happening,
mm-hmm.
you would really not want to get the read request to go to the same server where the write is happening, right?
We actually let it go to both. We could set things up so that writes go to the primary, reads go to the secondary. We actually let the reads go to both. I'm not sure if there's a really good reason for that. I mean, I can totally see why we might design things the way that you're talking about. One reason might be that we also have some sort of server-side processing where you can do like a function that actually runs on all the servers, and we want to be able to sort of minimize the number of servers it can run on. So sometimes it's helpful to be able to read from the primaries as well. I guess maybe it would be the best reason, but we could have done it that way. We could still do it that way in the future. Yeah.
All right. Thanks.
See a
All right.
question over there. Oh, okay.
One more, we could squeeze in one more.
Oh, all right, over here.
Yeah, thank you for introducing this geo. I have a question on the comparing this in the high level to the Redis cache, right? So because enterprise, my company like TD Ameritrade using the Redis cache as a solution, but I don't know like what is compare these two solutions. What your opinion about that, and the pros and the cons? Thank you.
Sure. I mean, so I'm not really an expert on Redis, so I might not be the best person to make this comparison. I believe, based on what I showed you guys today, I believe Redis actually replicates to the secondaries asynchronously. So they may have the stale read problem that I talked about. I think Redis is also single-threaded, so I don't know how that exactly affects the latency. I just saw something on Hacker News about, oh, somebody created a multi-threaded Redis and it was so much faster. Geode's already multi-threaded. And obviously the data modeling is very different in Geode versus Redis, and I think that we're storing objects there, you deal with all their collections. So that might be some things to start from, but there's probably other people that might be able to give you a better comparison that have actually worked with both products.